So if you came early, it would have already been recording, but I stopped it. And now I'm recording again. Just so the recording's not too long. Okay, stop share. And I gotta find the thing again. I lost us. Here we are. So our Canvas page is our Canvas page. The peer tutoring, I haven't heard anything more about that, but if you've looked into peer tutoring, maybe you'll know if somebody's there to offer some times for tutoring. Hopefully that's working out for you if you're interested. I have hours available every morning and every afternoon. So if you follow the instructions for Navigate, you can go in and sign up for an appointment. I think it has to be 24 hours in advance. I'll get notice that somebody signed up for an appointment, and I'll be here on Zoom to meet with you then, if that's, a one-on-one time is something you want. I posted our first lecture video here. I'll post this lecture video here-ish once it's done. It does take a little time to process. My son this summer session is taking calculus-based physics 2 as opposed to our algebra-based section, and he was having fun putting the professor on 1.5 speed while listening to the lecture. I highly recommend, if you go back and watch one of these lectures all over again, put it at 1.5 or double speed. I think you're familiar enough with the material that it won't be ridiculously fast, and I just like it better when I'm on double speed because I don't have to listen to myself so much. It's a weird thing for a lot of faculty to this past year for the first time, be in a position where we're watching ourselves teach quite so often. Sometimes it's a little disappointing. Sometimes it's good because I'm like, oh wait, did I say this thing backwards in lecture? And so I'll go back and watch the video and I'm like, oh, phew, I said it correctly. So I hate to confuse people. I got some word on lab number 1. The new simulation that they came out with doesn't have all the tools that were in the original simulation. So if you are working on that, just do the best you can, but I will go in and try to either update the instructions or the questions or something to try to make a little more sense with what's in there. I didn't get a chance to do that yet today, but that is a plan I have for later today. And then you can always click to the next page on the Canvas page into week 2, but if you're really excited to look ahead, chapter 13 and 14, the Canvas things are posted here on this main page. One thing you will notice, presumably, is the number of homework questions for each chapter is not the same throughout. If there's fewer key points in a chapter, I will just assign fewer homework problems. And if there's more, sadly, I will assign a couple more. You can probably bank on somewhere around 10 homework problems per chapter. looking, it looks like most people tackled the chapter 11 homework. That's good. So if you can just kind of keep up as we move along, you will be in good or better shape. A Tuesday, Thursday class has the benefit that Tuesday to Thursday isn't a long time, but then Thursday to the following Tuesday with a weekend in the middle seems a little bit like forever. Again, I would just advise knowing what reality is. I have a hard time getting anything done until right before the due date, but if you can somehow have it in your enthusiasm to finish the quiz today and then just dig in and see how much of the chapter 12 homework you can do right away. Because if you can get the chapter 12 homework done, then you can just review it before class next week to be ready for that quiz. But if you never do get to the point where you're doing the homework, if you put it off until next week, then it'll be worse because you'll be scrambling then and you'll be trying to remember whatever we talked about in lecture today. If you're able to discipline yourself enough to do that, I highly recommend jumping on the homework as soon as possible. That way things don't get piled up on you. Okay. View, reading view. As always, if you have any questions, feel free to just go ahead and ask them. I have chat open on my second screen, on my third screen. So if you have questions, go ahead and ask them. Otherwise, I will kind of boldly forge ahead into the world of fluid dynamics. And then I think I mentioned that this book, a lot of the algebra-based physics texts are geared toward students who are taking physics as a requirement for their hopes and dreams of going into the allied health professions. So the chapter just makes an effort to do some biological and medical applications because physics underlies everything. The word physician associated with a medical professional. Physics is everything, it really is. And I hope that as we go through the material, you're like, oh, wow, this really does have applications and this is interesting. And I'm so glad I'm taking this class and Dr. McTaylor is the best. I hope all of those thoughts go through your head. So we talked briefly about the fact that there's solid, liquid, and gas as the three primary states of matter. There's plasma as well, not blood plasma, but really hot stuff plasma. That's another state of matter. But the three regular old states of matter, solid, liquid, gas. Liquids and gases are both in this category of fluid. And a lot of what we're going to be doing right now is liquids, but we're soon to segue into some other applications, including the ideal gas law, which obviously is gases. So this is what? It's a segment of a pipe. It's a segment of a hose. It's a segment of a straw. Maybe it's a little segment of a vein or an artery in your body. What we're interested in is if you turn on the faucet in your house and water flows through the pipes and comes out the faucet, we're interested in the pipes have a certain diameter, measure all the way across, therefore a certain radius, which is halfway across, therefore a certain area. There's a certain area, the flat cross-sectional view area. And then if you measure a certain length, what you're going to get is a volume. There's a certain volume. So the area, A here stands for area. D stands for the distance, the length of the segment of the pipe. It doesn't stand for diameter. Diameter is capital D. Sorry that stuff is kind of obnoxious, but you have an area and a distance, and when you multiply area times distance, you get volume. And then what we're ultimately interested in is the flow rate, the volume flow rate or the mass flow rate. In practical terms, what you would probably do is take a bucket, a gallon bucket, and turn on the faucet full force and time how long it takes to fill up the gallon bucket, and then you would know a flow rate. Say you had to fill up your swimming pool from a hose, and you're like, oh goodness, how long is this going to take? Well, you'd get the total volume of the swimming pool, and then you go ahead and fill up a bucket, with the hose on full force to see how long that took. And then you could do a calculation. You could say, okay, it puts out 1 gallon in 30 seconds. So to fill a 500-gallon pool, it'll be 500 times 30 seconds, 250 minutes. And you go ahead and figure that out. So you'd have a sense of how long you're going to be sitting around with the hose flowing into the pool. That's just one idea. I mean, the other idea, any sorts of medical applications, if you have arteries and veins that have plaque buildup on the side, so they're a little diminished in their throughput, then there's some assessment for what is the flow rate through the less than ideal arteries and veins, that kind of thing. So flow rate is the volume of fluid per unit time flowing past a given point through area A. And chemistry is the science of how things change. Physics is kind of the science of how things stay the same. So one of the weird things with physics, we know that velocity equals distance over time. Well, we're coming up here with this idea that the flow rate, capital Q, is the volume that goes through divided by unit time, but volume is really just area times distance. So here we have a version of distance over time. Area times distance over time. Well, distance over time is velocity. So the flow rate Q is area times the velocity of the fluid. It's a convenient little substitution that we can do that would help us solve some problems later on. So there you have a little extra information built in. All right, so there's two typical kinds of flow. There's steady flow, and in steady flow, the velocity of the fluid particles at any point is constant as time passes. If you picture a gently flowing stream or a river, or I guess even, you turn on your garden hose and water just kind of comes out the end, or your faucet in the sink, water comes out. That would be steady flow. It's a constant flow. The other type of flow is unsteady flow, which an extreme kind of unsteady flow is turbulent flow. If you've been in an airplane and you've experienced turbulence, That's kind of the idea, that there's some unsteady pockets of air that are causing some issues with the plane going through it. Maybe an easier thing to kind of visualize would be like whitewater rafting, or just a very fast moving river, and you see the water like all over the place, crazy. It's not moving at a constant flow. Now, the weird thing about turbulent flow is that we take advantage of it in a lot of practical-ish circumstances. So turbulent flow, because the water, the fluid is just kind of moving around crazy, it doesn't offer as much resistance. If you're like trying to move against the stream in a river that's moving, smoothly, it takes a lot of effort because you're pushing against a constant push back on you. But maybe not whitewater rafting, but if you have unsteady flow, turbulent flow, you don't always encounter a molecule of water or fluid as you're moving through it. So it actually has less resistance. One of the weird aspects of this, I don't have one sitting on my table, is a golf ball. If you've ever picked up a golf ball, you will notice that as opposed to like a tennis ball, a golf ball has a whole bunch of little dimples in it. The dimples in a golf ball are there so the ball will travel further. There were originally, or at least some point in time, perfectly round, smooth golf balls, and those balls don't travel nearly as far when you hit them with your driver. It's the little dimples on the surface of what we normally think of as a golf ball that cause turbulent flow. As the ball's moving through the air encounters these little dimples and kind of goes off in strange directions, and that makes it so that there's less resistance, air resistance to the golf ball flying through the air, and it travels further. So now you know. That's one aspect of the flow of a fluid. So this is fluid dynamics, fluids in motion. That's one thing. Here's another thing to know about fluids, just in general. Fluids can be compressible or incompressible. Now, most liquids that you would deal with, brake fluid in your car, when you step on the brake, it's an incompressible fluid, which means the force that you're applying to the brake pedal is sent undiminished, maybe even magnified, but undiminished at least, to the brake pads that make your car come to a stop. Compressible fluids is something you probably don't think about a lot, but nitrogen gas, most of the air we breathe is nitrogen gas. And obviously there has to be some oxygen or we'd be in trouble, but most of what we breathe is nitrogen, not oxygen. Most of what we inhale to our lungs, the breathing part is oxygen. But nitrogen gas, if you squish it enough and reduce the temperature, it turns from a gas into a liquid. Liquid nitrogen is very cold. It takes up a lot less space than gaseous nitrogen. So there's compressed gases that you will see sometimes. Liquids, once you're in the liquid phase, it tends not to be compressible anymore, but gases, you can squish them. For fluid flow, it can be viscous or non-viscous. Viscosity is how sticky a fluid is. So I tend to think of syrup or like molasses as a very viscous fluid. It takes energy to get it to flow. And then a non-viscous fluid, I invariably think of a cup of coffee, because I can have my cup of coffee on the table and just bump the table really gently, I think, and my coffee splatters all over the place. So coffee, water, a lot of things are non-viscous, but the sticky kind of fluids are viscous. So just to kind of set our parameters for moving forward with discussion, we'll talk later about an ideal gas, but right now to talk about an ideal fluid would most likely be a liquid, incompressible and non-viscous. So those will kind of be the ground rules for how we approach the topic, and then there's exceptions to rules, as you're well aware. So we'll start with what we would call normal, the ideal fluid, and then some situations are changed a little bit if it's in non-ideal fluid. So talked about the steady flow, it's called laminar flow. Streamlines are used to represent the trajectory of the fluid particles. A lot of times in like engineering, I guess we get the Olympics pretty soon. You know, you want to reduce the amount of drag. So you'll notice the cyclists will have made some arrangements with their bikes to have as smooth a flow profile through the air as possible to minimize air resistance and get the most out of their riding. You'll notice the swimmers do all sorts of remarkable things to their caps and their shaving hair on their bodies and whatever to minimize drag going through the water. So we talked a little bit about this idea of mass flow rate. So it takes 30 seconds for a gallon of water to come out of my hose. That's with a given area. Now, if I change that area by like putting my thumb over the end of the hose, well, the same mass of water, the same volume of water, say a gallon of water, has to get through that smaller opening in the same 30 seconds. So when I put my thumb over the end, the water has to travel faster. And so you can see that if you ever mess with a garden hose and stick your thumb over the end of the hose and spray your friend with water. So this image appears in every physics book I've ever seen. It looks like you've got a wine bottle laying on its side with maybe a really long neck. But region 2 here has a large area, and then it goes into region 1 that's listed here with a much smaller area. So we're talking about the mass of fluid traveling through. Remember from our very first lecture, which was last time, that density equals mass over volume. So mass equals density times volume. But wait, volume equals area times distance. But then we have distance divided by time. So since velocity equals distance divided by time, then distance equals velocity times time. It's another way of expressing the distance. So kind of hold that thought in your head. So we get down here. So the change, the mass that will travel through in a given amount of time in area 1 is density times the area times the velocity. And then in region 1 here, density, area, velocity. Now, This is, when you put all that together, this is called the equation of continuity to discuss the mass flow rate at every position along a tube with a single entry and exit point. All of the fluid has to travel through. So all of the fluid is represented by the density of the fluid, the area of the region, and the velocity at that point. I guess 2 and 1. And so what could happen is the density could change and the velocity wouldn't increase as much. But we are going to do our equation of continuity with an ideal fluid. An ideal fluid is incompressible. So density changing is off the table. So we get this equation for an incompressible fluid, A1 V1 equals A2 V2. So all we'll need to know is the area of each part, which will generally be presented to us by giving us either the diameter or the radius explicitly. If we know the diameter divided by 2 equals radius, and then the area is pi r squared, pi times the radius squared. If we know the areas and we know one velocity, we can figure out the second velocity. Oftentimes it will be kind of phrased with the idea that, you know, the flow rate here is something, and then you put your thumb over the end of the hose and reduce the area by half. What happens to the velocity? And the simple answer is that it doubles. And then volume flow rate, we talked about that. So here's, you know, the example from the chapter. Remember that the units for physics are kind of mismatched with anything like reality right now. So we have a very small area because 2.85 times 10 to the negative 4th meters squared is still, you know, a garden hose. It's you know, a reasonable opening. And then we figured out that the volume, 8 times 10 to the negative 3rd cubic meters in 30 seconds. So we can figure out the flow rate, meters cubed per second. That's the volume flow rate. If we specifically want to talk about water, we can include the density of water and figure out what the mass flow rate is. But the whole point here is that we're going to reduce the area. So we can figure out the flow rate, area times velocity. So we can have the velocity be the flow rate, meters cubed per second, divided by the area. Figure out the initial velocity, 0.936. And then if we reduce that area by a factor of 2, we're going to double the exit velocity. Now, here's our wine bottle laying on its side. And here's something, there's an analogy with traffic on the highway. If you've ever been driving down the highway and then they take the 4-lane highway and block off 1 lane and then a 2nd lane, and then just for kicks, a 3rd lane as well. So suddenly 4 lanes of traffic have to merge into 1 single lane for a while they're doing road work. You will find that there is, in the region of 4 lanes, high pressure. There's a lot of frustrated people that are moving fairly slowly to merge into a single lane. And then once everybody's in a single lane, you discover that people move a lot faster. At least once it goes from 1 lane back to 4, the speed of everybody picks up a lot, and it's low pressure. So we have a high pressure region and a low pressure region. That happens in fluid moving across a flat pipe, even if the area of the pipe changes. There's also a thing, if you have a shower on the 2nd or 3rd story of a home, I guess even on the 1st floor, the water pressure comes in the basement, and then the water pressure in the 1st floor bathroom is about as good as it gets. But you go to a 2nd floor bathroom and the water pressure is a little bit lower. Why? Because some of the pressure, some of the work, energy that is moving the water through the pipes is actually lifting it up. Gravitational potential energy has to lift up the water to a higher height. And so the higher you get, the less water pressure you have, unless you do something remarkable to boost it back up. So this brings us to Bernoulli's equation, which I don't know if I mentioned this. If you've had me before, then you're well aware, but I'm not expecting you to memorize equations. I give you the equations you need on quizzes and exams. But I'm presenting the equations, and you may need to solve an equation for a certain variable. So just letting you know. So this is referencing back to Physics 1, non-conservative forces involved in work. And we have kinetic energy and gravitational potential energy. And so here at the bottom, the fluid moving through has both kinetic energy and gravitational potential energy. And then as it goes up, it will lose some of its kinetic energy as it increases in gravitational potential energy. So that's something that happens. So ultimately, Bernoulli's equation could give you a headache. It is a very long equation that is working for our ideal fluid, which is a non-viscous, incompressible fluid. And we'll find in 2 regions, perhaps with change in height, in 2 regions, pressure and then this kinetic energy piece, 1/2. Instead of m, we're going to use density for our fluid. Density times velocity squared plus density gy. So this is representing the gravitational potential component there. P1 plus 1/2 rho v1 squared plus rho gy1 equals P2 plus 1/2 rho v2 squared plus rho gy2. In reality, second definition. I'm not sure what that second definition is. Sorry about that. Every now and then I lose track of checking in on chat. So there was something that I went too quickly by. Sorry about that. But you have the PowerPoint and you have the video to watch when I get it posted. So non-viscous, incompressible fluid, these things are related. And typically, if you have one equation with one unknown, it's wicked easy. If you have one equation with 2 unknowns, it's problematic. And then like 3 unknowns, it'd be really problematic. So typically, anytime we're dealing with Bernoulli's equation, it will be simplified and maybe the pressure is the same on both sides. So pressure cancels out and you just have the other terms to think about. Or maybe it's traveling flat, so the height change doesn't matter at all. So typically Bernoulli's equation gets simplified as you answer a question. So I don't know, I never really noticed this when I'm driving down the highway, but if there's a truck with a tarp on top, supposedly you can notice that as it's driving fast, the tarp tends to bulge up into the air. Maybe you'd notice this with a convertible with the top up, if the top tends to bulge up. The idea here is just this relationship with velocity and pressure. The higher the velocity, the lower the pressure. So if the truck is driving quickly down the highway, the air that's moving on top of the tarp would be lower pressure than the air that's trapped underneath it, and the tarp would tend to bulge up. It's the same kind of concept that is used to describe the shape of an airplane wing. If you've never noticed how airplane wings are shaped, it's kind of a flat surface on the bottom and a rounded surface on the top of the wing. The idea is that on the top of the wing, as the plane is traveling through the air, that the air moving on top of the wing is moving faster, the air moving underneath is slower. Therefore, there's a difference in pressure, and that pressure creates this thing called dynamic lift, and it would cause the wing to want to travel up. Of course, it's also working against gravity, and there's all sorts of complications, but that's why the wings are shaped that way. We don't need to go through everything. If you're into games where somebody throws a ball, baseball or softball or wiffle ball, the idea with a curveball is that when you spin the ball in the air, on one side of the ball, you have higher pressure. On the other side of the ball, as the ball is spinning such that it's moving with the air molecules that are moving past it, you get lower pressure, and so you get this deflection, and the spinning ball will curve. All right. This is one of those classic examples. If you have a bucket with a hole in the bottom, on either side, it's open up to air pressure, regular atmospheric air pressure. So the pressure part of Bernoulli's equation cancels out. And so once you cancel out pressure, you can also say, all right, well, the rate at which the surface of the water up at the top is dropping will be negligible compared to how it's spilling out the tiny little hole. So if you count that velocity as essentially zero, and then go through the equation, you wind up with a much simplified version. 1/2 rho V1 squared equals rho GH. Well, the density is the same on both sides. So you can figure out the velocity of the water coming out the hole, because it's just the square root of 2 times the acceleration due to gravity times the height of the water surface at the top of the bucket. This is ideal, and it would be conservation of energy here, that if you arrange the spigot to shoot up in the air, it would be shooting up to the same height that the bucket is originally. I think now I have, some stuff that we're not going to get into. I decided at some point in my career that this material would be really interesting if you were going into engineering, but it's nothing that you ever do for like undergraduate science major. So I have it in the PowerPoint, but I don't have any questions based on it in the homework. So do not worry about some of these concepts. There's one other quick thing to mention. That is not in the PowerPoint. There is a thing, air is a fluid. It has density. You push your way through the air. We talked about that with like the Olympic athletes and how they would account for that. If you're skydiving, say, if you jump out of an airplane, you have your parachute on, but when you jump out of an airplane, you will accelerate at the acceleration due to gravity until you reach a point where the air resistance to you falling through the air is equal to your weight at that point. That's called terminal velocity. It's right around 100 miles an hour. If you hit the ground at 100 miles an hour, it will not go well. But you reach that terminal velocity and stay at that speed. You don't keep getting faster until you pull your parachute and then you slow down considerably. So in skydiving, there's that. And so there's a drag coefficient, and the equation for that and explanation of that is all provided for the homework question that includes drag coefficient. And that is enough for chapter 12 today. So take a moment, recover from all the fun we just had, and think a little bit about chapter 11. I have a quiz for you to take on chapter 11. It is based on the homework. Some questions directly from the homework, some questions similar. I'll also let you know that on the quizzes, if we were doing this in person in class, I would hand you a piece of paper, and that paper would have plenty of room for you to show your work. I love to give partial credit when you show your work. If you just write out an answer and it's wrong, I have no idea if you just guessed a number or what. So I can't give partial credit if you don't show your work. So I try to make it as not obnoxious as possible, but I leave a space for you to show your work. If you want to, and I highly recommend it, if you want to submit a photograph or a PDF or something of a piece of paper where you did your work, please do that. You don't have to do that for every individual problem. You can do it all at once. So maybe on problem number 1, where I say show your work, say I'll submit a photograph at the end. And then when you get to the end on the last problem, just attach the photograph. Some people have no problem whatsoever attaching photographs in the space I leave on the quiz. Other people have a problem. Just email me, either Canvas email or my regular salemstate.edu email, the image, and just let me know on the quiz. Oh, I will email you an image of my work, and I'll be sure to check that out when I'm grading the quiz. Okay, so I do have questions, and the questions I have are number 25. So, so here, force in over area in equals force out over area out. So what we want to figure out, the force in will be F1, So we want to figure out the force for the master cylinder that we're pushing on, and then the slave cylinder that lifts up the thing. So F in equals force out times, multiply both sides of the equation by area in over area out. All right, so force out is mg of the car, 2,000 kilograms times 9.8 meters per second squared. So force out 2,000 times 9.8, 19,600. Area, and hopefully this is kind of preparing you for a sad reality. If you're taking the MCAT or some other kind of standardized test, they're just obnoxious about things like diameter and area. So diameter, it's 2 centimeters. We want to convert from centimeters to meters. Then what you would do is say there's 100 centimeters in 1 meter. So I want centimeters to disappear. 1 meter is 100 centimeters. The other way to do this quickly is that centi stands for times 10 to the negative second. So this is 2 times 10 to the negative second, which is 0.02 meters, or 2 times 10 to the negative second meters. That's the diameter. Radius equals diameter divided by 2. So 2 times 10 to the negative second divided by 2 is 1 times 10 to the negative second meters. And then area equals pi r squared. So pi is just a number, 3.14159,265. Usually it's a button on your calculator. 1 times 10 to the negative second squared. So just be careful with your calculator. 1 times 10 to the negative second squared is 1 times 10 to the negative fourth times pi is 3.14 times 10 to the negative fourth. Oops, 10 to the negative fourth meters squared. It's area. Likewise for the other one, so a little bit faster, but the radius is 24. So 24 times 10 to the negative second divided by 2, so 12 times 10 to the negative second meters. Area equals pi times 12 times 10 to the negative second meters squared. 12 times 10 to the negative second is 1.2 times 10 to the negative first squared times pi, times pi is 4.52 times 10 to the negative second. All right, now we have all the pieces we need to figure out the Fn. So the force in equals force out, that's the 19,600 newtons, times area in, so that's the small one, 3.14 times 10 to the negative fourth divided by area out, 4.52 times 10 to the negative second. So 3.14 times 10 to the negative fourth divided by 4.52 times 10 to the negative second times 19,600, and I get 136 newtons. So yeah, that's
So I have
number
a question.
25. Any questions on that?
Yeah, I have a question. When you do
Yeah.
the negative, or when you do the 24 times 10 to the negative second divided by 2, where do you
Yep.
get that 2? Is it from the original 2?
Oh, from the centimeters,
Yeah.
the -2 centimeters. So I was converting to meters.
Okay. So for instance, if like my example is 1.7 centimeters, I would be dividing that by 1.7 as opposed to 2.
No. So if it's 1.7 centimeters,
Yeah.
it'd be 1.7 times 10 to the negative second meters. And then you divide by 2 to go from diameter to radius.
Okay.
So we needed to figure out the radius for pi r squared, and the information they gave us was diameter.
Okay. Thank you.
Sure. Okay, clear all drawings. That's the only question I see on my chat right now. Are there any other questions before you take the quiz? So if you go to our main Canvas page and scroll down a little bit, you'll come to the Chapter 11 quiz. You click on it, you get the rules of the game. You have 2 attempts. It will keep your average score. The first time, I want you to take it using just the data sheet that I provide and your calculator. You can take it a second time if you don't get a perfect score. Take it a second time to try to improve your score, and it will keep the average of the 2 attempts. All the data that you need, I believe, is here. If there's something you're missing or something you're confused about, feel free to ask. And when you're taking the quiz, you will find that there's a question and then a space for your work. And so you can upload an image there. You can type in what you did just so I can give you partial credit that way. And if you just want to upload one image for the whole thing, just say, I'm going to upload an image at the end, or email you an image, and that will be fine. Questions are identical or similar to the homework, and your numbers that you're using are going to be different from anybody else in the class because they change. But that's it. So I will go silent, and if you have questions for me, go ahead and type them in chat, and that's it. Take the quiz and then go about and have a happy day. So you can go when you're done, and I'll be here monitoring chat if you have questions, and I will post the video as soon as it gets done processing. So I'm going to stop recording now.